Alright, so we're going to be looking at the van der Waals gas, that's my American pronunciation of it. And this is the equation of state for van der Waals gas. Alright, so first we're going to use this thermodynamic relation. This is the internal energy with respect to the volume at a constant temperature is equal to T times, and here's the derivative of the pressure with respect to temperature at a constant volume minus the pressure, okay? Alright, so first what we're going to do is solve the equation of state for the pressure, because we're going to look for this quantity right here. This is what we're solving for. So we need to know the pressure here and the pressure here. Alright, so we'll start off just by saying P plus A over V squared equals, I'm just going to divide by V minus B, and KVT over V minus V. Let's switch to a different marker. This one's drying up a little bit. This one's a little thinner. Hopefully we can still see it. Okay, so, and now we have P is equal to this N KVT over V minus B. Okay, now we're just going to subtract by A over V squared. Alright, good. Alright, so when we take the derivative of P with respect to T, okay, this is holding volume constant, alright, because we need that for this piece right here. We are going to, alright, this term is a constant and just goes away, and all we end up with is this piece out here that's multiplied by T. So N KV over V minus B. Okay. Now, I guess what we really wanted was to multiply this by T, so let's just multiply both sides of this by T. And look, we end up with our term again, our first term. Okay, so when we calculate this du by dv, this, and this is a constant temperature, now we plug in our pieces. Okay, so first we have this, which is just what we got right here, and then minus the pressure. So minus that same term. Okay, we can see where that's going, and then minus this, so that's a plus A over V squared. All right, so these terms cancel out, and we are just left with an A over V squared. Okay, so now we are going to we're going to use this later, but so now supposing that the heat capacity CV at constant volume is independent of temperature, calculate the difference in energy between the gas with temperature T and volume V and a reference state of temperature T naught and volume V naught. Alright, so if we look at our change in energy here, we have the difference in energy with respect to temperature at constant volume multiplied by dt. Alright, this is just like chain rule stuff. And now we're taking a partial derivative with respect to volume at constant temperature, and with the dV here at the end. Okay, This derivative of energy with respect to temperature at constant volume, that is just CV, okay? All right, so this piece right here is just CV. So we bring down the dt, okay? And then, look what we have over here. This is du by dv at constant t. And that's what we solved for in part A, du by dv at constant t. So we can just plug in a over v squared from what we solved before, dv. Okay, so now what we were going to do is find the energy with respect to a reference temperature. So I'm going to integrate this. I'll just call this U diff. Okay, this is the difference in internal energy, right? All right, so we're integrating with respect to T here from the reference temperature T naught up to the T that we have, okay? And a CV dt, okay? And now we're integrating with respect to volume, V naught to V, A over V squared dV. All right, so now we just do this here integration. CV is a constant, so we get a CV and then the T minus T naught for this first term right here. All right, then we have a V to the minus 2 power here. So we raise it to a V to a minus 1 and then divide by minus 1. So we get a minus V to the minus 1 or a minus 1 over V. All right. And yeah, I'll bring that minus sign out here. Okay, so we had a minus 1 over V, and then that's evaluated at a V and V naught. Okay, and we could bring this minus sign in here and reverse those, but we'll just leave it as it is for now. Okay, so now this is again, the difference in, let me find that again. It's the difference in the internal energy between the gas with temperature T and volume V and the reference state temperature T naught and volume V naught. So that's what we found right here. Okay. All right, so now what we want to do is ask ourselves, how does the temperature change for free expansion of the van der Waals gas? So free expansion, you have, the classic situation is you just have gas in one half of a chamber and then you just punch a little hole in here and it just shoots out into the empty half of this chamber, right? That's the classic textbook example of this. Okay, so just starting with the ideal gas, the ideal gas has an internal energy of U equal to 3/2 N kBT. Right, for the ideal gas, as long as you're conserving number of particles and whatever, the internal energy is only dependent on the temperature. And for free expansion, there's no heating of the gas, there's no work being done on the gas, and the temperature stays the same, right? So let me just double check the question again. How does the temperature change for free expansion? Okay, so we're asking how does the temperature change for this free expansion? So for the ideal gas, again, for free expansion, the only way, so du is equal to times NQ dt. All right. Right. This can come from heat or work, right? For free, right? Du can come from heat or work. There's no heat being added to this, and there's no work being done. So du is equal to 0, therefore dt is equal to 0. And for the ideal gas, the change in the temperature is equal to 0. Okay. Long story. All right. Okay, so for free expansion, for the van der Waals gas, right? Now we have this difference in internal energy. Okay. Again, for free expansion, there's no difference in. Anyway, I think I messed up my words there. For van der Waals gas, we have this equation for internal energy. I think I said difference. Anyway, right, for free expansion, this, well, this is the difference. Anyway, it's between this, the temperature and the reference temperature, right? All right. So if we call the reference temperature like before the free expansion, and this T and V that we're looking at, that's after the free expansion, there's going to be no difference in the internal energy between those two. Again, no heat, no work. All right. Basically, when we look at free expansion, this is equal to 0 right here. Okay. So when we write this, I'm going to write CV. This is just the this term right here, and I'm just going to bring this term over to the other side. So CV multiplied by the quantity T minus T naught is equal to A, all right, 1 over V minus 1 over V naught, like this. Okay, so here we go. So the difference, what were we even talking about? We're talking about the difference in temperature of the gas for free expansion, all right? That difference in temperature is this right here, okay? So here we have the ideal gas, here we have van der Waals gas, okay? Delta T, okay? So here we have the ideal gas, okay? Right, for van der Waals gas, delta T is equal to, all we have to do is divide by the CV, like this, okay? All right, so there we go. This is the temperature change for van der Waals gas. Right, and again, van der Waals gas is just a simple model that includes some interaction between the particles. All right, so like a short-range repulsion and a long-range attraction, that sort of thing. All right, so when you have a free expansion of these, now that there's interaction between the particles, then they do care about the volume, like right here, right? And so let's just see. So if the free expansion, we were going from a small volume to a larger volume, so this would be a small volume and a larger volume. So 1 over a large, so this is a small number minus a bigger number, and delta T is negative. So basically it's cooling down as it expands.